Okay, let's get going. Okay, so before we start getting into talking about missing data, measurement error, how to do some of those sort of things in STAN, are there any additional questions that haven't been asked on Piazza about the homework for Thursday? Number of people have had some difficulties with this or that aspect of it. Another thing which can't remember if I mentioned it, but as part of like the workflow doing stuff in STAN, it's definitely advisable to start off when you don't know whether a STAN program is really going to work or not, to start off with like a smaller number of iterations or a smaller number of chains, like 1, or to set the max tree depth to something less than its default of 10. So it's not, if it's not going to go well, it's not doing like 2 to the 10th function evaluations per iteration until you get a sense of, okay, this is going to work or it's not going to work. And if it does, then, you can go ahead and you can run it with like the defaults or something close to the defaults to get like a bunch of draws from that posterior distribution. But if it's not going to work, to try to figure out why in a shorter amount of time. Another thing that you can do, especially if you're like making changes from a STAN program that is known to be working, and then you're going to make some changes to it that you don't know really if it's going to work, or you don't know if you've done it correctly, is to just like change one thing, run it for a little bit, see what the output is. If it's like similar to what you were getting before, except if it's different, maybe in a understandable way, okay, then change like one more thing, then change one more thing, and that helps you figure out, okay, here's like the relatively small change that I made that is causing like a big difference as to whether it works or not, causing a big difference as to whether it like goes in a few seconds or it goes in a few hours, things like that. So those are all things that you can get in the habit of doing. Other questions? Yes, Dan.
What if you do it with like 50 iterations and it still takes like 25 minutes to run?
So that is an indication that you can look at the Shiny STAN and whatnot for that, but that it's taking the maximum number of steps per iteration. And so that suggests, for some reason, it has to take very small steps in the leapfrogging part, but for some reason, maybe a different reason, it has to go a long way. Like the tails of the posterior distribution go out pretty far. So you have to take a small number of steps and you have a long ways to go, then it's going to take a large number of steps to get there. And so each iteration involves like thousands of function calls just to go through it. And it can take a fair amount of time to do that. But if that's the situation that you're in, and that's not necessarily the situation you anticipated being in, need to think about or look at the intermediate output, things like that, to figure out, well, one, why is it having to take such small steps? That has to be related to the curvature of the distribution being much more pronounced than like a normal distribution. Because if it was a normal distribution, STAN would be able to just do that in a second or two. And then relatedly, why is it that the tails of this posterior distribution go out so far? Why do I have to move so far to get from one part of the posterior distribution to the other, taking a bunch of small steps along the way? So if you could figure out why that might be, then you're in a better position to figure out, okay, what do I need to change in order to like get around that behavior? Another thing that I wanted to mention, I think caused a fair amount of confusion, is that in the original iteration of the Stan language, so this is going back to 2011 or so, the model blocks of a Stan program consisted of a lot of these statements where you have like y tilde normal parentheses mu sigma close parentheses semicolon. And the reason why it was done that way is because that was the syntax that the Bugs language, and the most popular variant of the Bugs language today is JAGS, specified models. So if you look at old WinBugs code or whatever, you'll see like y tilde normal mu comma tau or whatever. And so when we're developing the Stan language, or when we were first defining what the Stan language is, we basically used that same syntax because we thought at the time that the target users for Stan would be people who were fed up with bugs, but they wanted to do Bayesian analysis. And so we were trying to keep the syntax of Stan model blocks to be similar to Bugs model blocks. But that turned out to be a mistake because even though the Bugs people were some of the early adopters of Stan, they assumed that Stan was working the same way that Bugs was working, which is not the case, fortunately, because Bugs didn't really work for non-trivial posterior distributions. It can work for some very simple stuff. And so Bugs, Bayesian analysis using Gibbs sampling, really, as drawing from the posterior distribution, it's really draw from this distribution, then draw from that distribution, then draw from that distribution, where each of these distributions are the full conditional distribution of one parameter given all the other parameters and the data. So you like draw a value for the first parameter conditional on everything else, then take the realization of that first parameter, draw from the conditional distribution of the second parameter, given everything else inclusive of the draw that you just made of the first parameter, and then do the third. And so cycle through your variables each time, drawing from a full conditional distribution that is given or implied explicitly. The Bugs language had heuristics for figuring out what full conditional distributions your priors and your likelihood and stuff implied. So in that sense, the tilde notation basically meant draw from this distribution, or this thing was drawn from that distribution. And when you think about doing things in the Stan language, well, when all the things that we did on the first 3/4 of the semester, where we were drawing from prior predictive distributions, there was like normal underscore RNG. So you didn't just specify, okay, I'm talking about the normal distribution here. You're saying draw randomly from the normal distribution because you append the underscore RNG to it. So it's not just enough to say like it involves the normal distribution. You have to say, okay, is it the random number generator of the normal distribution? Is it the CDF of the normal distribution? Is it the PDF of the normal distribution? Etc. Those things. But anyway, you can draw from the prior predictive distribution using the explicit RNG functions that are provided in the Stan language, or you can create your own whatever. But when you go to draw from the posterior distribution using data that you didn't necessarily simulate, but data that you may have collected from the wild, putting those tilde statements in the model block, although it's still technically allowed, it's misleading, because when you put that stuff in the model block of a Stan program, it's not saying, okay, draw this from that distribution, draw this from this other distribution. what that tilde thing really maps into is the more explicit and more correct in the Stan context target plus equal notation. And so when you have wild data and you're trying to say, okay, I want the posterior distribution for these parameters conditional on the data, you need to define what that distribution is, because that conditional distribution is not in general going to have a name. It's some unnamed distribution that is the result of their priors and the likelihood and stuff like that. And so when you do all this target plus equal stuff, you're really defining an unnamed distribution for Stan to draw from using, no U-turn sampling and stuff like that. And the way in which those distributions are defined is by adding together logarithm of density functions or logarithm of mass functions in the case of data that correspond to the numerator of Bayes' rule in log units. So you're really building up this function that is defined in terms of log densities and saying, okay, at the end of the model block, after you've done all the target plus equal things, this is the definition of the distribution that Stan is drawing from jointly. So it's not like draw the first parameter from some distribution, draw the second parameter from some distribution. Really, you're just writing down a mathematical expression saying, Stan, use this to make a topology over the parameter space, and then use physics to move around through it in order to get joint draws from that posterior distribution that I defined using these density statements. And so putting the target plus equals, which is now the updated couple of years ago Stan language, is a more or it's less confusing as to what Stan is doing when you use that notation. And it sort of reinforces this idea that when you're drawing from the predictive distribution, given the parameters, then okay, taking the parameter distribution is known, then I'm just drawing from a Bernoulli, I'm drawing from a normal, whatever, I'm drawing from a Poisson in order to predict what the data will look like, either before I see the data or after I've gotten the posterior distribution, I'm predicting what new data will look like. So conditional on the parameters, those are just being drawn from explicit and named distributions. But when you're drawing from the posterior distribution, it's just this, joint distribution conditional on the data that doesn't have a name, but it does have a definition. And the definition is what you define it to be in the model block with all these target plus equal statements. So keep in mind the distinctions as to what is entailed when you're drawing from a predictive distribution versus when you're drawing from the posterior distribution of the parameters. And the main difference is when you're drawing from the posterior distribution of the parameters, you need to define what that distribution is. And so actually some of the comments in the Stan program for the first question on the homework, I'm not sure when that first draft of that paper came out, but anyway, it actually reinforces some of the wrong intuitions that Stan is like bugs. It basically says like, draw this, draw that, and that's not actually what's going on. Questions about that? Okay, so cool. Disclosure. I've already been talking about Stan, so this is perhaps should have said this earlier, but anyway, Columbia developed Stan. I use Stan. Lots of people use Stan. Some business sorts of people use Stan, like Facebook last week and stuff like that. And according to Columbia University policy, those things amount to expected earnings of $5,000 per year. I'm required to disclose these facts before proceeding on in a presentation. So before we get into missing data, which is actually the subject on the syllabus for this week, I want to talk about measurement error in the social sciences, which is sort of related. And so measurement error, I can understand why, but it's a weird phenomenon with the way social science works, particularly in academic stuff. So everyone agrees, and like no one disagrees, that the variables that are typically used in a lot of social science research are not measured very well. So there's an additional like layer of problematic stuff as to whether the things we're measuring correspond to the concepts that we're trying to talk about. But even like if they did something that is, you know, relatively straightforward, like income or whatever, when those are asked about on the social science surveys and stuff like that, everyone recognizes that the data that comes out of that is not a particularly great measurement of the person's income, even if you sort of are like very specific about what you mean, you know, income versus wages, or like, let's say you go through all that. But just the stuff that people tell you is not necessarily, it's necessarily not a great measure of their true income. So there's no disagreement about that. And it's not just income. You know, it's basically everything that we measure. Even something like pretty straightforward, you know, did you vote for Clinton versus Trump? If you're doing like retrospective stuff, there's some people that like legitimately don't remember. And then there's some people who, yeah, like they voted for Trump, but they don't want to say that now. So they say they voted for Clinton, even though they didn't. And, you know, we know those things are going on. And so basically all of the variables that are used in the social sciences are pretty suspect as to how well they measure the thing that they're ostensibly measuring. And there's no great, you know, controversy about that. Moreover, part two, it's been known for decades, at least among you know, methodologists, that measurement error is harmful, particularly for frequentist estimators. Now, there's a couple exceptions that I think are probably overly utilized, but it's worth going through what those exceptions are. So in like a plain linear, no link function, Gaussian model, best case scenario, you have random measurement error on whatever the outcome variable is. In that specific circumstances, ordinary least squares is still the best linear unbiased frequentist estimator. It's just the sigma that goes into that model includes both, you know, whatever omitted variables that you have, plus how much measurement error there is in the y that you're using. And so sigma is larger than it would be if there were, the true sigma is larger than it would be if there were no measurement error. But the estimates of the coefficients and the estimates of sigma are still unbiased, and it's the unbiased linear estimator with the smallest variance across data sets. So in that one particular case, random measurement error is not so bad, although the fact that the true sigma is larger means your estimated standard errors are going to be larger, your estimated confidence intervals are going to be wider, and maybe harder for you to reject a null hypothesis about this or that. But it's nothing really wrong with the estimator in an OLS framework when the outcome variable has random measurement error. So that is like the best case scenario. Same situation, if you have random measurement error on exactly one of the predictors, then the coefficient for that predictor is going to be biased towards 0. So if the true thing is going to be positive, then the estimate has an expectation that's less positive. If the true coefficient is negative, then the expectation of the estimator is going to be closer to 0 in the other direction. That's for the predictor that has measurement error. The coefficients of all the other predictors that don't have measurement error, they're also going to be biased due to the presence of measurement error in, you know, the first predictor. But the way in which they're biased, it's not a real obvious as to what direction that is going to be or how much of the magnitude is. But this, the second one, is considered, one of the better cases, even though it's still bad. So, if you're interested in the coefficient of the variable that has random measurement error in it, okay, it's biased towards 0. But if you do it and you still reject the null hypothesis, then okay, the true thing is probably even farther away, or in expectation. The expectation of the estimator is closer to 0, so it's reasonable to say that the true parameter is farther from 0. So it's sort of, as long as you can reject the null hypothesis, then maybe this isn't so bad. But that sort of presumes that your goal in life is to reject null hypotheses. If you wanted to do something, your utility was based on the predictions or something that come out of that model, then the fact that you have measurement error is going to make those predictions worse, and that can be bad for all sorts of reasons. So these both pertain to linear no-link Gaussian models, random measurement error, and random measurement error only affecting one variable, whether that's the outcome variable or it's one of the predictors. In literally every other situation involving measurement error, whether it's like a non-Gaussian model, you have measurement error, but it's not random. You have measurement error on multiple variables simultaneously. We know that frequentist estimators are going to be biased, but we can't really say how much, can't really say what the direction of the bias is, could go either way, could be big or small, and there's just not really a whole lot that you can say about it, either before seeing the data or after seeing the data, unless you make some pretty strong and uncheckable additional assumptions about the nature of the error and how it relates to the collection of variables that you have in the model. So social science, lots of measurement error, basically bad, well, never good. And there's a couple situations in which it wouldn't be all that bad, but generally speaking, bad. Now, as a result of that, measurement error considerations in the social sciences are basically ignored. It's like everyone gives everyone else amnesty on measurement error stuff. And there's, I guess, professional reasons why that might be the case. It would be kind of odd for a journal, let's say, editor in 2018 to say, this paper, the variables have measurement error. I don't really believe the conclusions. We're not going to publish it, when that journal has for decades been publishing empirical results for stuff in the social sciences involving variables that were measured just as bad, if not worse, in the past than how we're doing it today. It would be odd if a reviewer for American Political Science Review or Journal of Economics or something like that said, I don't think this paper should be published. The variables in it have too much measurement error, when that reviewer is submitting articles to that same journal that also have variables that are measured with a considerable amount of error, and saying, well, you should publish my paper. And so basically, you can read entire issues of journals in the social sciences and not say anything about measurement error or the consequences, and not even a defense that, oh, in this one case, the variables actually are measured really, really, really well. They don't even bother to say that. So we have a situation, lots of measurement error, lots of problems for measurement error, and very little discussion about it, very little action taken as a result of it. And it's basically just don't talk about it. Then it doesn't exist. Carry on as if these things were measured really well, because what are you going to do about it? Like that sort of defense, if one is needed, you know, I did as good a job as measuring the variables as I could. So let's just not talk about it anymore. And there's not much that can be done from a frequentist perspective. The only genuinely good thing that could be done, and this is basically what happens in the first scenario here, is to integrate out the variable that has measurement error in it, like frequentists do in a so-called random effects model, where we're thinking about, you know, the error term for Connecticut. You know, for all people who live in Connecticut, they have sort of this common component of the error term, and we're going to integrate that out of the original likelihood function in order to get a new likelihood function that doesn't have any state-specific variables in it. It just has variables that are common to everyone in the United States, and then we're going to maximize the likelihood with respect to the common variables, but by integrating out all the state-specific components of the error term, we allow for heterogeneity in the data generating process, and the estimated standard errors of the common coefficients across data sets take into account the fact that we have this state-to-state variation going on. And so one approach to measurement error would be to, you know, treat it basically the same way frequentists treat error components in a random effects context. And that entails all the same problems as it does with frequentist random effects estimators. Actually being able to do those integrals analytically is pretty much impossible, except in very rare cases involving Gaussians. You can attempt to do it numerically, but that is going to be numerically inaccurate and leading to not good but not well understood effects on the sampling distribution of the estimator if you try to do that numerically. Basically, the only good way of doing multi-dimensional integrals that can be done analytically is then to do MCMC, but then you're almost Bayesian if you have priors on the parameters and using MCMC. They don't want to do that. Moreover, even if you somehow get one of these things to work, it ignores the possibility that the true values of the variable may be one of the things that you're interested in making inference about, but you can't make inference about stuff that you integrate out of your likelihood function. You can only make inference about things that the likelihood, the new likelihood, is a function of, you know, that being the parameters. So there's not a whole lot of good options from a frequentist perspective, but in contrast, you take a Bayesian perspective, do a Bayesian analysis, you can incorporate measurement error into it with literally zero new concepts. You're just using the observed data, which may be mismeasured, to update your beliefs both about the true values of the data and the parameters that generate it in. So from the Bayesian perspective, there's basically just two types of things: things that we don't know, things that we do know, and we want to get updated distribution for everything that we don't know, given everything that we do know. And so if we let the stars indicate true data values that may or may not be observed, we let phi be a vector of parameters that pertain to the process by which the true data were mismeasured. And what we get is y, which is the actual observed thing, like what they tell us their income is, as opposed to y star being sort of their true income. Then we can write the posterior distribution for all the true values, theta, which is the parameters that go into the data generating process for the true values, and phi, which is a separate vector of parameters that governs the data mismeasurement process, why it is some are, overestimated, others are underestimated. Anyway, we can write this posterior PDF up to a constant, ignoring the constant in the denominator. Anyway, it's proportional to our prior beliefs about theta and phi, represented in terms of a PDF for them, multiplied by conditional PDF for the true data, given theta, the parameters that go into the data generating process, multiplied by a conditional PDF for the observed outcome that we actually have data on, conditional on the true data that Y is attempting to measure, and the parameters that go into, is that measured better or worse? Is there a tendency to overestimate, underestimate, whatever? Just using the general multiplication rule, we now have implied a joint PDF up to a constant for the theta, for phi, and the true data conditional on the observed data Y. And we can draw from that posterior distribution, at least conceptually, the same way that we would draw from any other posterior distribution. In a very special case, sigma or phi, if it represents sort of the standard deviation of the measurement error, let that go to 0. Y star and Y become the same thing. This PDF on the right here, the conditional PDF of Y given Y star, just collapses to a spike because Y and Y star are the same thing. So now you're multiplying by a constant here. And now we have, the same, setup that we had before, where we're just modeling, Y, because Y and Y star are synonymous, and phi is known with certainty. Rishika.
I missed the part. Why are Y and Y stars synonymous? I thought Y star is the data and Y is the data.
In general, they're not. But you can think about a limiting case where things are measured really, really, really well. And in that case, this basically becomes a spike. If phi represents sort of the standard deviation of the measurement errors, it's going down to 0. We know it perfectly. And so in the limit, all that's left over is theta and the likelihood for the true values, given theta. So, whether the measurement error is severe or not that much, whether it's random or, it has a tilt to it, it's very easy, at least in terms of math, to use the framework that we've been building up the whole semester and just incorporate the fact that we don't know the true data into it. It just slides right in. So, with the frequentist thing, basically very slim to none in terms of good options. With the Bayesian thing, at least conceptually, there's nothing new. Even if things were measured perfectly, you would have to use the Bayesian apparatus to update your beliefs about theta. And so if you're in a situation where you have measurement error, which is to say, if you're in a situation, then you might as well update your beliefs about Y star and phi along with it. Questions about that? Please.
I'm not sure if I understood, in the frequentist method, what the integrating out really does.
Okay, so if you can do it, and you take, there's no priors, of course, but you take these two things, and you integrate out theta star, you now have a function involving just Y and theta, and you could choose theta to maximize that.
And usually we don't know about the measurement.
Yeah, correct. So that's usually impossible, but you could think about trying to do it numerically or something like that. But basically, because in order to do maximum likelihood estimation, one of the things that's a necessary condition for those estimates to be consistent is the number of things to estimate has to remain fixed as the number of observations goes to infinity. Now, if you introduce the idea of measurement error, basically every time you add a new observation, there's another unknown, which is the true value for that observation. So the number of things to estimate also goes to infinity. And in that case, maximum likelihood estimators did not produce consistent estimates of anything. So you really need to be able to integrate out the Y stars in order to leave yourself just estimating theta. But that's really not practical. Becca.
So, E put a prior also on fee, right? The idea?
Yes.
So in the Trump scenario, we might say, oh, we think that people are not going to admit that they voted for Trump, so we think U is like less than 0 or something.
Yeah, so it can actually, it's a little easier to think about with continuous variables, at least to start. But if you're talking about something discrete like that, you basically have 4 possibilities. They said they vote for Trump and they actually did vote for Trump. They said they voted for Clinton, but they actually voted for Trump. The other way around, they actually voted for Clinton, but they said they vote for Trump now, and they actually voted for Clinton and they said they vote for Clinton. And so you have, instead of like 2 possibilities, which would be the case if everything was measured perfectly and people were being honest and stuff like that, you now have 4 possibilities. And so you need to think about the conditional probability of saying that you vote for Trump now, given that you voted for Trump 2 years ago or a year and a half ago, whatever. And you know, the other 3 going into that, and phi would be the parameters in that aspect of it.
You have it for each of those. You need a different prior for each of those.
Yeah. Right. So, I mean, technically you need a joint prior for all the parameters or whatever, but it may often be the case, or at least reasonable to be the case, that your beliefs about theta are independent of your beliefs about phi.
But broadly, phi is something you say, I think that there's measurement error in this direction, and that is how I define it.
And how much, yeah. So let's, maybe simplify it a little bit, random measurement error. Phi could be the standard deviation of your measuring instrument. Or it could get more complicated than that. Yes?
How are we updating our beliefs about phi if we never see any stars?
The conditional distribution of phi is, even if the priors between theta and phi are independent of each other, conditional on the observed data y. Nothing is independent of anything. So theta is in the posterior distribution is dependent with phi. Y star is dependent with theta and phi. So by updating our beliefs about any one thing, we update our beliefs about everything that's not independent of that. And that is the same kind of idea talked a little bit about in the Humphreys and Jacobs paper, like how can we update our beliefs about like these clue probabilities if we don't, the phi actually in there, and we never actually observe what they are. It's because we have this joint distribution of everything conditional on the data. The data are more informative about some aspects of it than others, but the fact that in the posterior distribution things aren't independent. If I get information about one thing, that tells me more information about anything, provided they're not independent of each other. So perhaps it would be good to see how this is represented in stand code. So here's a simple case, stand code for regression that has error in its predictor. You could do this with multiple predictors, but just to keep it simple, we only have one predictor. So we have n, the number of observations. We have x, which is what we observe x to be, how we measure x. And then we have some observed outcomes y, which in this case will presume to be measured correctly, or if not, then it just goes into the error standard deviation from 1. And the parameters block, which, you know, perhaps in this context, it would be better if it just called like unknown stuff, exogenous unknowns, whatever it may be. Richard, you know, has a point about this, that, you know, the distinction between, you know, parameters and latent data, or parameters and true data, or parameters and data that's missing the true values of it. There's not really a hard distinction between these things. There's just stuff that's unknown, and there's stuff that is known, such as n, and we do know what we observe on x. We don't know that if it's like how close it is to the true x or whatever, but we have the data that comes back in the survey. Anyway, the unknown parameters is a vector of size n, which I'll call z, which is going to represent the true values of the predictor, but in standardized form. We have unknown expectation for x, the true predictor, unknown standard deviation for x. And then we have this additional parameter tau, which I perhaps should have called phi, or it's among the things that would go into phi if this is a more complicated thing, which is constrained to be positive, and it's the standard deviation of the measurement error in x obs. So all of this kind of pertains to the mismeasurement process. And then we have the regular stuff that we would have for the true data generating process, what we would have done before if everything was measured perfectly. So we have an intercept, we have a coefficient. This should be lower equals 0 right there. And then we have standard deviation for the errors in y. Beta could easily be a vector of coefficients, and we could have multiple predictors measured with error, etc. So then in my model block, I have a local vector of size n, which I'm conceptualizing as the true value of x. I'm using the mat trick, the property of the multivariate normal, or the normal distribution, that it's in the scale location family. So I can take z, which is my unknown, but it's in standardized units, multiply it by the standard deviation of x, shift it by the mean of x, and now x has a priori a normal distribution with mean mu and standard deviation sigma. Then the only sort of additional line that I really need in my model block is now I'm defining the distribution that I'm drawing from with this additional contribution based on, you know, normal distribution, or I could have used t or, you know, anything else. My observed measurements of x given the true x, normal, true x is my expectation of what I measure x to be, and then I have tau, standard deviation of, in this case, random measurement error in x. To make this work well in STAN, you are going to need an informative prior on tau, expressing your prior beliefs as to whether the measurement error is going to be like big or huge. But once you have that, then you're good to go. And then the remaining thing, basically a likelihood statement, y, the data generating process for y involves the intercepted coefficient multiplied by the true x. So, you know, the real data, whatever the outcome is, according to our theoretical model, driven by the true x, not what we measure x to be. Now, in some situations in the social sciences, like the outcome actually depends on what people sort of perceive the x to be, or like what they think the x of somebody else is. But, you know, in the simple case, we're thinking of the data as being generated according to the true x, and it has some standard deviation sigma y. We have a prior on z that it's standard normal. This implies our beliefs about x. It's normal with mean mu, standard deviation sigma. Then we need priors on alpha and beta and sigma y, especially on tau. But, you know, you can use whatever you want there, more target plus equal statements. And that's it. So in this situation, if we try to do OLS, our estimate of beta would be biased toward 0. If you do it the Bayesian way, We're not saying anything about the behavior of this across like bunches of data sets, but with the data that we have, the X's that we observe, we can get a distribution of updated distribution of beliefs about alpha, beta, and everything else. And it is coherent. It is the rational thing to believe given the data that you have, however flawed it may be. Sebastian.
So if you did the thing where you cohort people, but you sort of most expensive equipment subset that we were way.
Yeah, so presumably with the more expensive equipment, you would have done some calibration or whatever to get a really good sense of what tau is. Like if you didn't use that equipment, like with the same people, you measure them with the expensive good equipment and the crappy equipment, and you know, you see. And so you would presumably have like a really good belief about tau. And then, you know, you have a bunch of people that were with the less expensive equipment. And then presumably the tau applies to them. Yeah. It's really not that hard. Andres.
Maybe where are you finding the prior for the parameter?
I didn't for alpha, beta, and sigma y, or mu x and sigma x. I just said, do it. It can be whatever you want. And here's where this is interesting. So you could call this a prior for z. You could call this a likelihood statement for x obs, but you're really just saying like, this is my posterior distribution, draw from it. And it doesn't really matter what you call prior, what you call likelihood, because in log units, it just all adds together.
And tau, you said no.
Right. So you're going to need a prior on tau. If you say like, you know, tau could be any positive number and your prior is like uniform over the real line, then this is probably not going to work well. And because your posterior distribution might not even be proper if you use the improper prior on tau. But basically, in order to get anything from this, you need to have a pretty decent sense of how bad the measurement error is. If you have like literally no idea, then probably your updated beliefs about alpha, beta, and everything else are going to be very diffuse. Because if tau could be anything, then x could be anything. And you know, if x could be anything, then alpha and beta can be pretty much anything. And so you might not be real happy with your posterior distribution for alpha, beta, and everything else if you provide virtually no prior information about tau. But that's the coherent, rational thing to think. If you really don't know how well this is measured, you really don't know anything about tau, then you really should be very uncertain about alpha and beta and everything else, because you're uncertain about what even the predictor is. Questions? Yes.
Can I get much super clear, please? But I don't fully understand why the standardization of X observation. Standardization of the
Right. So this sigma x is basically like the standard deviation of true x in the population. How much your x differs from somebody else's, the true of it. Tau pertains to how well or poorly we measure your x and everybody else's with our measuring instrument. And so it may be the case that, this thing doesn't vary that much from person to person. In that case, sigma x would be small. But we may measure it very badly for everybody, in which case tau could be big, and our observed values of x are very spread out. Not because that's the way people actually are, but that's because our measurement is not that good. Or it could be the other way around. people, countries differ a lot on things like, democracy, but we have, better or worse ways of measuring that. And so, sigma X between like all the countries in the world, probably pretty big, but, we might measure it okay. But we definitely want to update our beliefs about how well we're measuring democracy with these, various measures that people collect data on. Marlon? If you extend it to nonlinear cases, yes. You just, you have some nonlinear mechanism relating x obs to x. So maybe, for like income, you tend to undermeasure the income of rich people, let's say. That's pretty widely held thing. So what we observe, what people say their income is, might very well be related to x and x squared, to have some nonlinear mismeasurement in the data measurement process, where we tend to underestimate the income of rich people and overestimate the income of poor people, or something like that. So really, you just got to define what your posterior distribution is, and then you have a good chance of being able to draw from that posterior distribution. So these
question related to an earlier question. So in this program, we are not defining the right of time.
I left it open, but I said you need to have one.
Okay. So if we do that, we do that in the
Yeah.
And say, okay,
right. All the target plus equal things, those happen in the model block. Model block defines the distribution you are drawing from as the sum of a bunch of pieces in log units. Define the distribution. If it's continuous, Stan has a good chance of being able to draw from that efficiently. And if you can't do it in Stan, you probably can't do it with anything, at least today. Okay. So rounding. Even concepts that are supposedly continuous in the social science, when we measure them, we often sort of round them to the nearest unit, or the nearest 100, or the nearest 1,000, or something like that. Depending on how big or small things are, even just rounding can make a difference. And so if we wanted to do a model where, let's say, the outcome was, rounded to the nearest integer, we have n, we have k, we have x, which is the n by k matrix. We have our observed measure of y, but we know y, according to the data generating process, has been rounded to the nearest integer. We have an intercept, we have coefficients, we have standard deviation of the errors, and then we have a vector of size n. That is the rounding error. I've bounded that between -0.5 and +0.5 if I know the data have been rounded to the nearest integer. Then I could construct in my model block what I believe to be the true y, which is observed y rounded to the nearest integer, plus or minus something between -0.5 and +0.5 from the rounding error. And then my beliefs, the data generating process, true y was intercept plus predictors times coefficients, rather than observed y, which has this weird discretization to it due to the rounding and sigma. You're going to need priors on alpha and beta and sigma here, but having, in this case, if we're just talking about plus or minus 0.5 in here, having, uniform between -0.5 and +0.5 on the rounding error wouldn't be the worst thing in the world. And it's probably harder to do much better than that. So again, pretty simple to overcome the effects of rounding to the nearest integer. using a Stan program, and your little bit of uncertainty as to whether, this thing was like, what you observe plus a quarter, plus a third, minus 0.43, whatever. Your uncertainty as to what the true underlying continuous y would be is being propagated to your posterior distribution on alpha and beta in the appropriate Bayesian way. Again, not too difficult, unless you try to do this with OLS. Questions?
Doubts about numbers like 10 to 100.
Oh, they're round numbers, but it's not an explicit like we rounded it to the nearest one. More challenging, definitely, than this. So maybe a little bit of a simpler case. Let's say you have like these feeling thermometer things, and you can say like between 0 and 100, and it's basically continuous. But there's a lot of people that say 0, and a lot of people that say 100, even though that just sort of represents their like have extreme views on those things. Not that it's really not that it's measured like that, or it even has relevant units. What I like to do in a situation like that is like an ordinal sort of setup where you can either say the minimum value, some intermediate value, or the maximum value. It would like an ordered logit, and then conditional on you having an intermediate value, then like beta distribution for the intermediate people. That doesn't explicitly have to do with measurement error, but that's one way in which a pretty common situation in political science where you get this like clumping on conspicuous values thing could be handled, stuff like that. But basically in a situation like this where people are like saying round numbers, even if it's not explicitly rounded, the marginal distribution is going to be this spiky thing. And so you need to choose priors and a likelihood and a measurement process that, when you draw from the prior predictive distribution, also has this spikiness to it. And then you know that, you have a good chance of being able to capture some of this aspect to it. But with all these things, you need to really think about the process by which the data came to be in your possession, and then try to deal with the problems that come up with that. So another of the problems, also very common in the social science, is for some data to be completely missing, rather than just having like a rough measure of it is. People just don't say at all what the data value is. And missing data basically cuts to the heart of the frequentist definition of probability, and it precludes any way of really considering this in a satisfactory way. Now, remember, frequentists define the probability of A is the number of times that A occurs divided by the total number of replications, so the sum where A occurs plus the count of the number of times that A does not occur, as the total number of replications, n goes to infinity. Okay. But what if for some proportion that's non-zero of the n independent trials, we don't know whether A happened or not happened because that value goes missing. In that case, probability of A is undefined, or it's not defined as a unique number. You could maybe put bounds on it by assuming like all the ones that were missing are counted as A, or all the ones that are missing are counted as not A. You could get a range of what the probability of A is. But having a range for the probability of A doesn't really mesh with the frequentist framework, where all these sort of limiting things presume that the estimator is converging to a constant. When if you have missing this, there's no exactly fixed constant for this to converge to. So another thing you can do, and this is basically what people do a lot, you can assume that the proportion of times where A is missing is the same as the proportion of times that A occurs in the observed data. So that's basically to say that whether A is observed is independent of what the true A is. And so that's what people do a lot. But then you're basically expressing your beliefs, but just phrasing it as an assumption rather than a beliefs about, you know, the missingness in A being independent of the values of A. The good thing to do, if possible, is to, you know, treat it like measurement error, treat it like a random effects model, integrate out the true values that are missing from your likelihood and maximize it with respect to everything else. But that is not generally going to be possible to do analytically, and it's not generally going to be practical to do numerically unless you use MCMC. One of the things people are tempted to do, and we talked about this earlier, well, can I just maximize my likelihood over the true values that are missing and the parameters theta? But in that situation, the number of parameters to estimate is going to be going to infinity as the number of observations goes to infinity, assuming there's some non-zero proportion that are going to be missing, in which case you're going to get inconsistent estimators of everything. And so, you know, just like with missing data, or just like with mismeasured data, it doesn't really go with the frequentist framework that well. Mismeasured data is very common in social science. Missing data, just as common in social science. And so the way in which frequentists even define probability makes it, you know, very difficult for them to have attractive options as to what to do when there is missingness or when there is measurement error. In contrast, with the Bayesian approach, once you sort of understand how we update our beliefs about theta, well, it's the same process when you're updating your beliefs about the true values of the data. You know, if that's mismeasured or some of them are missing. But there's one additional thing with the missing data stuff. So we think of the true values of the missing data are unknowns. We have prior beliefs about them. We can update those to posterior beliefs, expressing everything in terms of probability distributions. Basically, you know, mismeasured data, you can think about that as the extreme case of missing data and, you know, the Y stars and stuff. But when you have sort of data because people refuse to answer, the government refuses to make some information available, you can think about this n by k binary array, which we'll call R, and the cell in the ith row in the kth column of R is 1 if the kth variable is observed for the ith observation, and it's 0 if the kth variable is missing for the ith observation. And so we always know what R is fully. It's just zeros and ones. Nothing in R is missing, but R encodes whether, you know, some column of X or, you know, for some person is, or Y, whatever is missing. So if we separate out the concepts XM and XO to indicate missing data and observed data, then we have theta, the parameters for the data generating process. If we observed everything, we have phi being the parameters that go into, you know, why is this value missing for some people, observed for others. Then we can write Bayes' rule as, you know, giving us a posterior PDF for theta, which we're probably most interested in, are functions of theta. Phi, which governs the missingness process, the true value of the data that go missing, and we want to get that posterior distribution conditional on the observed data and R, which is this n by k array telling us what's missing, what's observed. That posterior can be written as, you know, proportional prior on theta and phi, then multiplied by a PDF for the missing data, the observed data, and R together, conditional on theta and phi. And often we're going to go further, factorize that one more time. Prior on theta and phi, a PDF for the missing values and the observed values together, given theta, and another distribution for R, given phi and the union of the missing value and the observed values of the data. So again, just using the multiplication rule, we're getting, you know, updated beliefs about both theta and phi and xm. Only difference from the mismeasurement error case is, in general, we want to be conditioning on R in addition to conditioning on the observed values of x. So R gives us more information about everything that we can utilize in order to get more precise posterior distributions about these things. And it goes, well, go to the next slide. So there's sort of two ways of going from here that are talked about in the literature. One is known as the selection factorization. Another is known as the pattern missingness factorization. The selection one is used a lot more often. So we just pick up where we left off on the previous slide. We have priors for theta and phi. We have what Rubin calls the complete data likelihood. That is not just the likelihood of the observed thing, but rather, you know, if you assume there's a normal data generating process, you assume it pertains both to the missing values and the observed values, conditional on theta, whatever the parameters that go into that. And then the other part of this gets multiplied by a PMF for R, conditional on phi, the parameters that go into who's missing, who's observed, and the union of the missing values and the observed values. So some acronymonology here. We say that a data generating process is missing at random if and only if it is the case that our beliefs about theta are independent a priori from our beliefs about phi. That's a pretty weak assumption. What is a strong assumption that you could make from here is to assume this last piece, the missingness model, does not depend on xm, the unobserved values of x. It only depends on phi, the parameters, and things that are observed. If that's the case, if it simplifies down like the missingness doesn't matter here, we say that the data generating process is missing at random. And moreover, a further special case, the data generating process is missing completely at random if, in addition, the missingness model, it doesn't even depend on the observed values of x. All it does is depend on some unknown parameters, phi. Do not confuse missing completely at random, which is often abbreviated MCAR, with missing conditionally at random, which is not a thing. But if it were a thing, it would be abbreviated MCAR. And if it were a thing, it would mean what missing at random actually means. So missing at random is basically saying xm doesn't matter conditional on xo. But there's no C in missing at random. If a data generating process is neither missing at random nor the special case of missing at random, which is missing completely at random, the data generating process is said to be missing not at random, which is abbreviated IMNAR, and that means the same thing as not missing at random, which is abbreviated INMAR. So IMNAR and INMAR mean the same thing. Missing at random is a special case of, or it's a limiting case of this general missing not at random thing where we have the XM doesn't matter in the missingness model, and then missing completely at random is a more extreme assumption where R doesn't even depend on the observed values of X, it just depends on phi. You can think of missing completely at random as just you're flipping a biased coin as to whether the thing is observed or not. The coin doesn't have to be 0.5 probability of heads and tails. You can estimate what the probability of it is as speaking. Anyway, if the data or process is missing at random, then you can write this whole posterior distribution as proportional. Well, there should be a prior in here, but anyway, the likelihood part of it. We have a piece for the theta and the missingness values conditional on the observed values. And we have a separate piece for phi given R. And these two pieces are independent of each other, in which case you could update your beliefs on the first part separately from your beliefs about the second part, or maybe just not even update your beliefs about phi at all. You can make inference about theta and m by itself. That doesn't mean just drop the data and just focus on this. It basically means if it's missing at random, it is in theory possible to integrate out XM and do your inference about theta, but it may not be possible to do that analytically. Anyway, you'll see a lot of stuff people do saying, I assume it's missing at random. And we'll talk more about what those things are on Thursday. But basically with Stan, it's easy to just not worry about all this acronym stuff. Just do each part of this in the model block of your Stan program. And if it turns out that XM doesn't matter, then you'll just get some coefficient that's near 0 in a logit model predicting whether R is 1 or 0. On the basis of the union of the XM and the XO. So we'll talk more about that on Thursday, but are there any quick questions about that before we take off? Yeah, Rob.
So for missing at random, it's okay for there to be a different probability of an observation being missing, different values of the observed predictions?
Yes. It basically just means, okay, the way it comes in practice, let's say you have some variable that's basically fully observed and probably observed pretty well, like age. And then you say conditional on age, which is fully observed, let's say income conditional on age. So income is going to have a lot of missingness. But if that missingness only depended on age and age was fully observed, then it would be in a missing at random situation. The probability of being missing on income does not depend on income itself. But that is dubious because no matter whether you're old or young, we think we know that, richer people are less likely to tell you what their income is. Poorer people are less likely to know what their income is. And so actually, in reality, whether R is 0 or 1 depends not just on age or even not primarily on age, but actually on the true value of income, in which case you would be in a situation where the missingness is not at random, IMNAR, or not missing at random, INMAR, which are the same thing. Yes. Look.
So the completely at random stuff kind of sounds like a trick that frequencies. I don't know.
The frequentists do some stuff, but it's actually Bayesian. We'll talk about that on Thursday. Yeah. So all the multiple imputation stuff, that's really a Bayesian thing that they trick the frequentists into thinking is frequentist. Other questions about that? No? Okay, we'll pick it up on Thursday.
question.
Yeah.
I did everything we talked about. I just want to make sure I'm interpreting